This is also called as alternator. Alternator. So we have a machine that runs at a slightly comparatively more speed. Okay, so machine that is running at a higher speed, I will write higher speed, is called as a turbo alternator. Is called turbo alternator. So basically, the turbo alternator has some details added to it. It can come in an issue like turbo alternator. So the machine that will have lesser number of poles, this will have less number of poles. Okay, and it will have the length of the poles. In this case, for a turbo alternator or high speed alternator, I can write high speed. Okay, so it has less number of poles. The other factor that is important here is it has large axial length. Okay, large axial, or I can say a longer axial length, that is longer axial length. And the third factor involved here is it has a small diameter. It has a small diameter for rotor. Okay, so the axial length will be considered for the rotor. Okay, so this is the only machine where you have in a synchronous machine. If we revise it, so if you look at synchronous machine, so this is the only machine that runs at synchronous speed, that is at ns. Ns is equal to 2f by p. Okay, so ns, the speed will become large from this formula only. Frequency is fixed. Okay, 50 hertz for India and 60 for US. Now, can anybody tell me why it is 50 hertz for India and 60 hertz for US? Has this thing arisen into your mind? Yeah, tell me. Anyone can answer it? Ratika, do you know? Ratika? Ratika, are you able to hear
Yes,
me?
sir.
Can you tell me why it is 50 hertz for India and 60 for US? Hmm? Manohar, can you tell? Manohar, are you there? Nilinakshi, can you tell me? Nilinakshi. Nilinakshi? Okay. So we have Chaitra is there, Ajit is there, Bipul is there, Manohar is there. So anyone, can you tell me why 50 hertz for India and 60 hertz for this? So essentially what has happened, if you carefully look at the Indian system, so Indian everything has come, power lining, railway line, everything has come from the British. Okay. So it has deep roots in history. Prior to the British, there were Mughals, but at that time there was no power and all that thing. Okay, so it came from the British. If you carefully look at the British numerical system, so they have this one, two, and five. They have adopted one, two, and five. So what happened is US, why they have taken 60 hertz? If you will carefully see, 60 seconds is equal to 1 minute. So they have taken according to this. That's why they have kept this at 60 hertz frequency. But British wanted to be something different from them. So their currency also, if you see in India, it will be either 1 into 10, 10 rupees. Okay, 1 into 20, 20 rupees, or 5 into 10, 50. You will not get a 30 rupee, 40 rupee, 60 rupee. You'll always get in multiples of these. You will get 1 into even 2000 you have. 500 also you have, even you had 1000. Okay, so 1 into 1000. So this is the reason they have adopted this 50 hertz, and they had went for the 60 hertz. Now carefully you look, that was a small thing that I wanted to tell you. So this speed will increase only if the number of poles is less. So that is there, less number of poles, then only you can see speed goes up, because ns is equal to 2f by p. Then a larger length. So this type of construction is called as the turbo alternator. Now, there is another type of construction that is known as the hydro alternator. That is known as the hydro alternator. Okay, hydro alternator. No. In case of the hydro alternator, if you will take the hydro alternator. So hydro alternator is basically what? Hydro alternator will have lesser speed. Okay, like turbo alternator has a more speed, whereas your hydro alternator will be having a larger speed. So when we'll be considering the hydro alternator, so in that case, so the number one thing there would be it has a lesser speed. In order to have a lesser speed, automatically the number of poles are more. So to have this decreased, you have to increase the number of poles. So the first criteria that I'll be writing down there is, so the number one factor here is number of poles are more. So number of the poles are more. This is for hydro alternator, that is a less speed machine. Okay, less speed machine. Okay, the second factor that we will see in a hydro alternator, that is our second factor, would be to, the second factor is the, here they had large axial length, whereas here there would be a smaller axial length. Okay, smaller axial length of the rotor, length of the rotor, it would have a small axial length of the rotor. And the third factor that is here is you have small diameter of the sorry, see here, longer axial length and small diameter, it will have a larger diameter, larger diameter. Okay, so this will be larger diameter, and number small axial length, larger diameter. Okay, so these are the factors that you see encounter in a synchronous machine. So these are two type of synchronous machine. And see the rotor construction, one is called the cylindrical pole machine and another is non-cylindrical pole machine. So cylindrical and non-cylindrical, that is silent and non-salient. So these are the two constructions which we have previously also studied. So today let's do about the output equation of a synchronous machine. How do you go about it? So let's derive the output equation of synchronous machine. So while you are deriving this synchronous machine, so okay, like machine. So the number one thing that you require over here is, see, first of all, whenever we are considering going for the output equation, what we do is that we take the this q is equal to 3 times e phase I phase into 10 power minus 3 kVA. So this is the thing, this is common in all the machines. So here what we do is that since it's a three-phase machine, let's consider, because 3 came from the value of this, or either otherwise we can write m into e phase I phase in 10 power minus 3. Okay, so one more question to me is that why we are only considering 3 phase, why we cannot go for a 6 phase, okay, 12 phase, 48 phase machine? Why only 3 phase? Can anybody answer me? If you carefully go for the rail wheel factory of India, that is rail wheel factory, now I think the name changed, rail wheel factory, where the wheels of the rails are manufactured. It is located in Bangalore, Yalanka. Okay, I have done my final year project there. Bangalore, Yalanka. If you go out there, I don't know nowadays they give permission or not. In those days, I got the permission to do my project. So there you will encounter a 48 phase, 48 phase system. Now, why they have this 48 phase system is that because they want the amount of power that is required to melt iron will not be met with the three phase system. But most of the work that we require today has is met with the three phase system. For example, our three phase machinery and all that thing, whatever work we want. But for melting iron, three phase won't do. So they have to separately install a polyphase system, that is a 48 phase system. So that's the reason the three phase and the single phase system is common, because that much amount of work we require. If we require more power and more energy for melting iron and all, three phase would do. So we have to go for a higher system. So it's not that only three phase is available there. We go for a polyphase construction also. So here, since that we have to derive the output equation, I'll write M. M later on I'll take 3. So consider M phase machine having one parallel path per phase, and kV of rating of the machine is this. So I'll write down, consider consider M phase machine having one parallel path, one parallel path. Okay. So now important thing is that from here E phase I know, like E phase I can write in terms of the quantities which I have derived previously. Also in the induction machine also we have utilized this. So this would be we have seen this is 4.44. Okay, F phi. Okay, T phase. Okay, and the winding factor Kw. So this is the formula for this for induction machine. So this E phase value I can substitute in equation 1. Let this be equation 2. So I can substitute this in equation 1, and I can get uh, Q equal to, instead of substituting 2 in 1, so I can get what? Instead of E phase it would be M. For the time being, let's write M. Instead of E phase, right, I will write this 4.44 F phi T phase Kw, and here I have my I phase, and I have my 10 power minus 3 kVA. So this is the 10 power minus 3 kVA. So yeah, wait, something. Yeah, are you able to see my board? Yeah, Ratika?
Yes, sir. Yes, sir.
Okay, board is visible, but something is coming on the side, isn't it? Or it's not for you? Are you only to see? Wait 1 second. I have some issues here with my. I don't know what. Okay. Now are you able to see the board?
No, sir.
No, na. That's what I was wondering. So take some time. Wait 1 second. Yeah, now. Now you are able to see, right?
Yes, sir.
Okay, okay. We will not disturb the setting. Otherwise, I'm okay. Okay, this is kVA. Now another thing is that in this value of F we can substitute. So the value of F, we know that F is equal to what? In terms of we can write it P ns by 2, because we just now saw your ns value was equal to 2F by P. From that only P ns by 2, F would be P ns by 2. So F value here I can substitute. If I write this as equation 3, I can substitute from equation 4 in 3. So equation 4 in 3 if I put, so I get one value. So this value would be M. Okay, this value would be M into 4.44. Instead of F I will write P ns by 2. Okay, and I have my phi over here. Okay, T phase Kw into I phase into 10 power minus 3 kV as usual. So I saw that value over there. So this is my value, and F I got from this particular F from this equation 4 I substitute there. So let's take the thing from this. So if I can write this PNS by 2 phi T phase K phase, I can insert inside. See, I have this what do you call this M. Okay, and PNS value I have. So what I can do is I can divide here 2 ones are 2.22, or I can write this like this. So 2 into 1.11. Okay, if I write over there, so I can write m is 2m into 1.11, and the rest quantities. Okay, rest quantities, that are these quantities. So when I have to substitute this back, so I can write it in terms of this. Okay, so what I have done is that I can write it in terms of 1.11. Okay, kW P5, and this 2m, 1.11 I took outside, 2m inside. Okay, I phase, T phase inside, and one more thing that is missing is ns into 10 power minus 3. So I can write this in terms of this. So once I wrote this in terms of this, so I'll take this into the next slide to understand. So let's take it into the next slide. So I get this in terms of, so the Q I get like 1.11, 1.11 kW, 1.11 kW P5. Okay, 2m I phase, T phase, ns into 10 power minus 3. So ns into 10 power minus 3. So now what I can see is that now current in each conductor, like in each conductor, if I consider is iz, that is equal to I phase. Okay, so the total number of armature conductors. Okay, total number of armature conductors z, that is, this is the total number of armature conductors. So the total number of armature conductors will depend upon what? I have already told you previously also, we have discussed z would be equal to number of phases. Okay, number of phases into twice number of turns. Number of phases, if it is m, and this is 2, and number of turns is 2 phase. So this z value is equal to, z value, if you can see carefully, z value is equal to 2m t phase. So here you can see there is 2m t phase. Instead of 2m t phase, we can write z over here. So again the equation will change. 1.11 kW P5. Okay, this will become z. Okay, 2m t phase, z into I phase. Okay, into ns into 10 power minus 3. So the equation is changing. Now once we have done this change, so we have a value z into I phase. So z into I phase is basically the electrical loading of the machine. Okay, so z into I phase, so we can write your z into I phase is nothing but as equal to 2m t phase, that is the value of z into I phase. So this is the electrical loading, that is ampere conductors. Okay, this is also the electrical loading. Okay, so there are two things that are happening: magnetic loading and electrical loading in every machine. So this is the total electrical loading, that is iz by z, or I phase by 2m t phase I. So this thing I can write this, if my I phase is equal to iz, so here I can write 2 into, instead of I phase I can write iz, no problem for me over there. So now I have to resubstitute into the equation, wherein my equation will reduce 1.11 kW P5 Iz into Z ns into this thing. So now what is P phase? See, this is the, this term Z into this is called electrical loading. Okay, electrical loading, wherein this term is the magnetic loading. This is the magnetic loading. So if I have written BAV, okay, many a times I have written BAV. BAV is what? P5 by area, area by dl. Okay, so P5 I can write in terms of BAV into pi dl. So this is BAV into pi dl. So in other terms, P phase is equal to B average pi dl. So instead of P phase, I can write BAV pi dl. So once I'm writing this, so my equation again changes. So my equation will change, and now my Q becomes 1.11 kW. Instead of P phase, I have BAV pi dl. Okay, this Z into I phase will remain as it is. Okay, or I can also write Z into I phase in terms of ampere conductors. Okay, so see, if you see carefully, P phase is equal to pi d L BAV, and similarly your Iz by Z would be equal to the total diameter, that is 2 pi circumference, that is pi d, or 2 pi r you can write, because d is equal to 2r. So you'll write pi d into the ampere conductors. So instead of Iz by Z over here, this term you can write pi d into ampere conductors. Here you have ns into 10 power minus 3. Now you resubstitute. So this is basically the magnetic loading here, and this is the electrical loading over here. So these two terms, this is the magnetic loading and electrical loading, and you are substituting back. So you notice that you will arrive at the equation, final equation would be, your Q would be equal to, this is final, Q would be equal to 1.11 kW. And what you do is that pi, here there is one pi, here there is one pi, so pi square. Okay, here there is d, here there is d, so you can write this d square also. Okay, so you d square, let that be so here you have BAV. Okay, so first write BAV, here you have AC into AC. Let me write it like this kW, let it be here kW, uh, into 10 power minus 3. Okay, what are the other terms that are left? See here, d into d square. Other term L is left, L ns. So you already know in the popular literature, this term inside here is what? This term is what? Tell me. This is called C naught. Okay, this is C naught. So again, you got it in form of C naught d square L ns. So if you have to write this equation, so it will be again Q would be equal to, Q would be equal to C naught d square L into ns, where C naught is equal to what? It is equal to, C naught is equal to, see, C naught is equal to 1.11 pi square BAV AC kW into 10 power minus 3 into d square lns. Now if you do 1.11 pi square, it comes nearly around 11. Okay, it would 10.9 or 10 something, so we'll take this 1.11 pi square approximate to 11 BAV AC kW into 10 power minus 3 d square lns. So this is the value for this particular equation. Now if you want to write it in terms of the peripheral speed, okay, so this equation, you can see this is the output equation, this Q is the output equation. So what is the peripheral speed? Okay, peripheral velocity, you tell me. Can anybody tell me in terms of peripheral speed? So I want this equation, this is an assignment. The last chapter also I have not assignment for all of you. I'll put in the assignment for all of you. Write this equation in terms of peripheral speed, in terms of peripheral peripheral velocity. So now let's do one simple problem and get our better understanding. So how we will do. So more or less whatever till now what we have studied is the same thing. So we are saying that if you are familiar, if you do one equation or induction machine properly or DC machine properly, and the basics are clear, so most of the equations are relevant. Okay, this is not something really very difficult, just a slight modification, that's all. So let's do this problem. Okay, so uh, three phase 30 pole. So this is a three phase 30 pole, 3.3 3.3 kV, y connected, y connected, y connected salient pole, salient pole, alternator is designed designed to supply is designed to supply a uh, rated current of 130 ampere with average flux density of 0.55 Tesla, 0.55 Tesla, and the specific electrical loading and the specific electrical loading. So the specific electrical loading of 3000, this is 3000 ampere conductor, 3000 ampere conductor per meter. So if the conductor per slot, that is if the conductor per slot is equal to 9, okay, 9, and slots, okay, per pole, per per phase, per phase is 2. Now find kVA rating of find kVA rating of alternator, find kVA rating of alternator, then main dimensions, this you have to find width of parallel slots, that is your width of parallel slots, this is the width of parallel slots. Then if the flux density, that is your average flux, if the flux density is 1.8 Tesla. So how do you go about this problem? Basically, so the solution to the problem is, first you have to go for the given data. Okay, so the given data is like, there you have the given data. So the number one thing is the Q value, that is 3.3 k. No, Q value is not there. This is the voltage value they have mentioned, 3.3 kV. Okay, now it is Y connected, so you have to divide that voltage by root 3. Salient is designed to supply a rated current of, so rated current is IZ is equal to 130 amps with a average flux density. So this is V average is equal to 0.55, the flux density 0.5, and the specific electrical loading, that is ampere conductors AC, is equal to 3000. Okay, if the conductors per slot, that is conductors per slot, okay, that is your ZSS basically, okay, is equal to 9. Okay, and slots per pole per phase, this is the Q value. Okay, slots per pole per phase, find the kVA rating. So what you have to find, Q value you have to find. Okay, main dimensions you have to find. D and L value you have to find. D value, L value you have to find. Width of the parallel path. So W D width you have to find. If the flux density is now, this is the question. Now if the flux density of the tooth is equal to 1.8 Tesla, let's go for the first point over here. So Ratika, Afsa,
Yes, sir. Yes, sir.
are you following?
Yes, sir.
Are you? Oh yeah, yeah. Are you? Because I'm yeah. So how do you do then? So first of all, you will write the kVA rating. Okay. For the kVA rating, you know the value of Q. Hmm? Q is what? So Q will be equal to C. Q is kVA rating was what in the previous question only. You do the kVA rating very easily. Okay. So Q value we have seen in the very beginning. So this is 3 E phase I phase in 10 power minus 3 kVA. Okay. This was about the kVA rating. So here like it's a three phase machine. So already they have mentioned the value of Q. So the value of Q basically you can directly substitute the values. Okay. So kVA rating here would be direct multiplication. So the for the kVA rating he has given it is 3.3 kV for Y connected. So that means already has incorporated the for because this is for the three phase. So this is M. So this you have to directly write 3.3, and this value is I phase he is directly given 3.3, and I phase is equal to 130. So if you do this, so 3.3 it you will get around 429 kVA, isn't it? Are you getting? Hmm? 30 339 390 09. Okay, you will be getting the value, and this is 3.3, so you're getting 4.290. As mentioned, it is 3000. Then kW value, if kW value is not mentioned anywhere, remember, so you take this value as 0.955. So into here I don't think they have mentioned it, so you have to take, because it's a standard value, 0.955 in 10 power minus 3. Once you do this, you will get around 17.33. Okay, so we got, now we have to go for the main dimensions. So in order to go for the main dimensions, so what you will do, again you have this particular formula for getting into the main dimensions. That is, see, main dimensions, you know, d square L is equal to Q C naught NS. So Q value you calculated 429. Okay, C naught value is also there, 17.33. This is 17.33. Now you know you have to calculate the value of ns. Ns is equal to nothing but 2f by p. So it will be 2 into 50 number of poles. How many number of poles are there in the machine? Tell me. How many number of poles? Poles we have y connected is 3 pole, 30 pole. So number of poles we forgot in the given data, p is equal to 30. So you have to write down this data and substitute it there. So it would be divided by 30. So it is 100 divided by 30 of 10 by 3, that is 3.33. Okay, this is your 3.33 rps. So these substitute back, you must be thinking it's looking like just like the induction motor thing. So if you master over one thing, one or two problems, so it's more or less the output equation and all more or less same. Okay, so again you substitute this 3.33 429. This is an VTU exam problem. It's come for around, I'll just check. It's come for 8 marks in VTO. Okay. So most of the problems which I have taken are from VTU exam. You can cross refer so that you have this confidence whenever you are going to the, and some of the problems are of that sort only. So we get this value. This value we get around 7.434. It's an meter cube. So this is the value we are getting, around 7.434 meter cube. And now there is something, uh, we have to get the value of this. Okay, now if we carefully look at the problem, why connected cell is designed to supply rated current with a large flux. Okay, everything is there, but how to separate this D and L? Okay, so for DL and separation, just like in case of induction motor, so for best power factor usually we design, for here also we will do for the same. So whenever a synchronous motor question comes and there is no mention of the power factor, so you take the L by Z ratio or L by tau ratio is equal to 0.65. So that is, there are some assumptions that are required. That's why the problem becomes little. But if you already know these assumptions like kW value 0.955 and this L by Z ratio, so it will become very easy for you. So I'll take 0.65. In some books they will write L by tau. Okay, why? Because Z is equal to total number of conductors, and if we write Z here we will get confused. So we will also take L by tau only. Okay, so tau is what? Pi d by p. So we know that the tau value is pi d by p. So this is 0.65 into pi d by p is equal to L. So here again L is equal to 0.65 into pi, p is 30 by d. So if we resubstitute, we get around L is equal to 0.68. L is equal to 0.068 d. So this value you substitute there, d square into 0.068 d would be 7434. You can calculate the d cube value is equal to 109.32, or d is equal to 4.78, and L is equal to 4.78 uh, into what? 0.068. So this L value you'll get around, L value you will get around 0.325 meter. So now you got these two values, L value and D value. So the D value which you got was around 4.78 meter, and the L value you are getting is around 0.325 meter. So the peripheral speed, okay, which we have previously also seen, peripheral speed, or you can say velocity, peripheral speed or velocity, this would be equal to pi dns, pi dns. So pi value, d value is given there 4.78, your ns value you have equal to 3.33, which you have calculated. So your peripheral speed is va is equal to 49.9 meter per second, which is less than 60 meter per second. Now why? See, that means in case of this machine, in the induction motor, so minimum width of the turn, so we have to calculate this width of the turn and this minimum, this happens to be around 5 divided by slots per pole, okay, into length into 1.8. So this is the standard formula to calculate the width. Okay, width per pole for a velocity less than 60 meter per second. So this thing is there. So again you have the bav value you can recalculate p5 divided by pi dl. So your p value is there, okay, or you can get your phi value from there, because you don't have a phi value, so it will be bav into pi dl, okay, divided by p. So if you want to calculate this value bav into pi dl divided by p, so the entire value would be bav already mentioned in the problem, 0.55, 0.55 pi, you know, d you just now calculated 4.78, l you also you calculated 0.325, number of poles you know 30. So if you calculate this value, so you'll get around your flux would be equal to 0.0894 Weber from this particular equation. So again, you have been told your slots per pole per phase is equal to 2. So you have been told your slots per pole per phase is equal to 2. Again, slots per pole. So if you only want to calculate slots per pole, okay, per pole, that would be 2 into phase. So 2 into phase is 3, it would be equal to 6. So now, just like the induction machines stuff, so you have to calculate the slot pitch. So slot pitch is basically your ys, that is pi d by ss. Ss is the total number of stator slots. Now if you want to get the total number of stator slots, total number of stator slots would be equal to, see, here if you see slots per pole, just saw slots per pole was equal to 6. Okay, so total number of stator slots would be equal to, slots would be equal to 6 into number of poles. So from this, so number of poles is 30, so total number of slots would be 180. So you know this value is 180 over here. So d value is already you calculated from the above expression. Okay, so that value you know it's is equal to 4.78, and this total number of slots is 180. So you get this pitch around 0.0834 meter. Okay, so one more thing, last time also I told you about this formula, net iron length. So all the material will not be required, so there is some 90% material used and some wastage. So the net iron length required in this particular equation, we have to go about this net iron length. So now net iron length, so net iron length required, this net iron length required would be equal to Li, that is equal to Ki into the total length which you calculated minus, okay, your ventilating ducts, that is NV, and your width of each duct. Okay, so I will write down net iron length, where this is the Li is net iron length. Okay, NV is the number of ventilating ducts, ventilating ducts. Okay, and your BV is width of, BV is width of each duct. So BV is width of each duct. So three ventilating ducts, each of 10 millimeter wide is provided. So we see all the ventilating duct, so its width is 10 mm. So this NV usually by default it is 10 mm. So you have to take, and this Ki value also I told you, it is the ratio, that is 0.9, that is 90%. In one problem we have seen previously. So if you revise or go to the YouTube channel or go to the drive link, I have put all my videos there. You can go there and revisit it if you have any confusion. So 0.325, okay, minus, okay, 3 into 10 into 10 power minus 3. So this is the formula basically, wherein 0.9 comes for Ka. Okay, length is 0.325 which we calculated. Now we have how many ventilating ducts, it's a three-phase machine, so we have three ventilating ducts, and each duct is having a width of 10 mm. So NV is the number of ventilating ducts that we require, that is 3, and BV is the width of each duct, that is 10 mm. So so this is for this and this for this. Okay, so once we get the length, now this is the actual length, that is 0.266 meter. Now we require to calculate the width. So in order to calculate the width, what we require is here, if we go back to the problem, so we'll just go. So what does the problem read? See, a three-phase 30-pole 3.3 kV connected silent pole alternator is designed to supply a rated current, okay, with density this Tesla and the specified electrical loading of this thing. Find kVA rating of the alternator, main diameter, width of parallel slots. So this width you have to calculate. Width of parallel slots if the flux density. Now here, if you carefully notice, the flux density is changing 1.8 Tesla. So it's mentioned over there. So that is why when we were calculating the thing, we had to incorporate this width also. So that thing over there, when we went for the minimum width, so minimum width is like we have to incorporate for the BAV value also. So WT minimum was 5 divided by S by P plus Li into 1.8 over here. If you see here, over here 1.8, I thought I missed this point. So this is 1.8 over here. Now after recalculating this value, here we had calculated this equal to 0.894 Weber. So this was due to the length, okay. Therein we substitute the original length, but when we have to go back to this problem, so slots per pole was 6, okay, but now the length has changed, okay. Here we have seen, so now here if we revisit here, so now this length has changed. Earlier it was that length 0.325. Now this length has changed and it has become 0.26 millimeter, okay. So therefore, because we have incorporated the wastage and other factors and the width of ducts and all, so therefore the minimum width would be, again, formula will remain same. What is the formula? Phi divided by stator per pole into the length, okay, but this length would be the net iron length, okay, net iron, and your flux per pole, that is already given over there, was equal to 1.8, so that would remain same only here. So you have the value of flux, okay, you have the other things calculated, so you write directly 0.894 divided by 6 slots per pole 6 into 0.266 into 1.8. So once you calculate this, you get the value of 0.031 meter. So now you want to know what is the width of the slot, okay. So width of the slot would depend upon what? So he is asking to calculate the width of the slot. See here, see, find KVA rating of this main dimension, width of the parallel slot. So width of the slot would depend upon two factors. So it would depend upon the number one thing that we calculated over there was the ratio, that is your WSS. So the WSS that we calculated was pi d by stator slots. So that pi d by stator slots value was around, see, that is called slot pitch. So your width of the stator slot would be your slot pitch, that is the width of the slot pitch, minus the width of this what we say, minus the width of here we calculated, minus this minimum width that is required, okay. So the total width would be, like, for example, the total width would be your, if you have to calculate the width of the slot, so of slot, so slot would be inside basically the slot pitch, okay, and width of the slot. So if I draw like this, so okay, so this is like you have to calculate this. So in order to calculate this here or there, or this width, width over there. So we have to go for the total width, and see, this is width of the slot would be equal to basically your slot pitch minus the minimum width you calculated. Okay, so your slot pitch minus the minimum width, it would be the width of the slot. So slot pitch was 0.8 0.0834 minus 0.031. So this would be the width of the slot, that is 0.0524 meter. So this can also be told as the maximum width of the slot that is present. So this is equal to ws max. Okay, and this is 0.0524 meter. Now if you carefully look my previous examples and cases, so you will be able to follow it. So this the width of the slot, that is the, here if you see, actually what happens is that you have this, I'm not able to draw it properly. So you have this. Okay, so this is the width which you want. Okay, so from, wait, from here to, from here to here you have this slot pitch. Okay, wss, and this is the what do we call, this is the ws that you need to calculate. Okay, and this value is wt minimum. So you want to calculate ws. So ws, if you can see, wss minus wt minimum. Now it looks fine, huh? So you got my point. Yeah, are you able to hear me, Ratika? Ratika,
Yes, sir. Yes, sir.
you got this by this diagram, you got it.
Yes, sir.
So this was about the question. So I'll revise it because only 4 minutes are left. We cannot take any other topic. So firstly, what we saw in today's lecture was like how to derive this output equation, and we got the values in terms of c square dlns. Okay. Apart from that, then I went for a problem over here, wherein it was very simple. We had to calculate the kVA rating. kVA rating would be E phase into I phase. Here also we can write basically 10 power minus 3, no, not needed, because already it is given in kV. Okay, that 10 power minus 3 is required because we that must have been in volts. That's why we convert it into kV. That's why we require 10 power minus 3. You might be wondering why he did not multiply. And one more thing, why 3 value he has not been multiplied, because already he has mentioned the three phase voltage is this. Okay, in terms of kVA, so we directly multiplied these quantities. So you have to be careful how he has mentioned over there. Okay, so and other factors he what he has mentioned. So basically that thing you have to keep into mind before doing the problem. Then you have to calculate the main dimensions. So main dimensions, straight away d square L Q C naught ns value calculated, C naught value also. So d square L you got. So we took a condition for best power factor L by Z. If you have any other ratio, but it should be related to for optimum design or for something. So write it down like L by Z you have considered for this case. If there is no mention in the question, you can write, you can take any value of L by Z, but it has to be relevant to some value. You can write it down, you can take, answer can be different, no problem. D and L value can be different based upon this design. That's why it's called electrical machine design. Okay, so for what factors you are designing, in the very beginning I told you in the very first lecture on what factors we are designing. For economy we are designing, for best power factor we are designing, for best efficiency we are designing. There are so many categories for which we are designing. If there is no mention, you can take any L by Z ratio, but it has to be there with the statistical data. Get the value of D and L. Okay, so that is whenever main dimensions is asked, that means you are being to answer D and L value. Then you have to calculate the width. In order to calculate the width, what you do it is the width formula you wrote. This earlier also I have taught you. So you wrote it in this particular form, got this answer, and then you substituted it, you got a slot pitch. and then you resubstitute it to get the length, and this length you resubstitute back in that formula. Then you have to get the width of this plot. That was your YSS minus WT minimum. So if you have any doubts anywhere, you can please tell me now itself. Or you have any doubt? Yeah, Ratika? Any
No, sir.
doubts? So shall we wind up? I'll stop recording. Wait, where to stop this? You can give the attendance. Okay.